What if everything we thought we knew about the universe was just the tip of the cosmic iceberg? Picture this: somewhere out there in the vast, swirling expanse of space, there could exist a phenomenon so strange, so utterly defiant of the laws we hold sacred, that it flips own equations on their head. These are white holes, the universe's best-kept secret, a cosmic enigma that doesn't just bend the rules, it shatters them. While black holes devour everything in their path, white holes do the unthinkable. They spit matter back out, like a cosmic fountain spraying stardust into the void. And here's the wildest part. What if these elusive objects aren't just theoretical curiosities, but the missing pieces to the greatest puzzles in physics? For decades, white holes existed only as scribbles in the margins of equations, dismissed as mathematical oddities too bizarre to be real. But now, a growing chorus of scientists is daring to ask, what if we've been wrong all along? What if white holes aren't just hypothetical? What if they're hiding in plain sight, woven into the fabric of the cosmos itself? Some researchers even believe these cosmic rebels could hold the key to understanding the Big Bang, suggesting that our entire universe might have burst into existence from a white hole's explosive birth. It's an idea so radical, it could rewrite the story of everything. That's exactly what we're diving into today: 26 of the most controversial, mind-bending hypotheses about white holes. Theories that push the boundaries of science into realms once reserved for science fiction. From the possibility of white holes lurking in the aftermath of black hole deaths to their potential role as gateways to other dimensions, we're about to explore ideas that challenge the very foundation of physics. So if you've ever stared up at the night sky and wondered what secrets it's still keeping, get ready, because this journey will take you to the edge of human understanding and beyond. The universe is stranger than we ever imagined, and the truth might be waiting where we least expect it. Imagine the Big Bang not as a single cataclysmic explosion in the distant past, but as an ongoing cosmic event, one that might still be unfolding around us in ways we've barely begun to comprehend. This is the radical idea at the heart of Hypothesis 1, that white holes could be the lingering echoes of the universe's birth, remnants of that primordial singularity still actively pouring energy and matter into the cosmos. Think of them not as relics, but as living, breathing fragments of creation itself. The traditional view paints the Big Bang as a one-time spark, a moment when all of space and time erupted from an infinitely dense point. But what if that point never truly disappeared? Some theorists argue that the singularity didn't just vanish, it fragmented, leaving behind cosmic shrapnel in the form of white holes. These objects wouldn't just be leftovers, they'd be active participants in shaping the universe, continuously releasing the energy trapped during those first explosive moments. Picture a firework that never stops bursting, its sparks still dancing across the sky billions of years later. If this hypothesis holds, it would force us to rewrite the entire story of cosmic origins. Instead of a static, fading echo from the past, the Big Bang might be more like a symphony with movements still playing out. Some researchers even speculate that these white holes could explain mysterious energy signatures detected in deep space, pockets of radiation or particle streams with no clear source. Could these be the fingerprints of creation itself, still imprinting itself on the universe? The implications stretch far beyond mere curiosity. If white holes are indeed remnants of the Big Bang, they could hold clues to the universe's ultimate fate. Are they slowing down, or will they keep feeding the cosmos indefinitely? Could they be the reason our universe keeps expanding at an accelerating rate? Each question unravels another layer of the mystery, turning what we thought was a settled chapter of physics into an open-ended saga. And if we ever find one, a white hole glowing quietly in the void, it wouldn't just be a discovery. It would be a window straight back to the beginning of everything. But what if white holes aren't just cosmic leftovers? What if they're the universe's ultimate escape artists? Hypothesis 2 takes us down a rabbit hole where black holes and white holes might be two sides of the same cosmic coin, linked by a process so strange it defies classical physics: quantum tunneling. Imagine a black hole not as a one-way street to oblivion, but as a hidden passageway, a cosmic wormhole where matter isn't destroyed, but smuggled across spacetime to re-emerge in a dazzling burst from a white hole. It's like watching a magician's trick on a galactic scale. Matter disappears into the void, only to reappear somewhere else, unharmed and unchanged. This idea isn't just science fiction. It's rooted in the cutting-edge mathematics of loop quantum gravity, a theory that reimagines spacetime as a woven fabric of tiny, indivisible threads. In this framework, the crushing singularity at the heart of a black hole might not be the end of the road. Instead, the insane pressures could trigger a quantum rebound, a sort of cosmic bounce that transforms the black hole into its opposite, a white hole. Think of it like squeezing a spring to its limit. Eventually, it snaps back with explosive force. If this is true, every black hole could secretly be a white hole in disguise, waiting for the right quantum moment to reveal its true nature. The implications are staggering. For decades, physicists have wrestled with the black hole information paradox, the nightmare scenario where matter and information vanish forever, violating the fundamental law that information can't be destroyed. But if black holes funnel their contents into white holes, the paradox vanishes. Information isn't lost, it's just relocated like a letter mailed across the universe. Suddenly, the cosmos looks less like a collection of isolated objects and more like a vast, interconnected network, with black holes and white holes serving as cosmic transit hubs. Even more mind-bending, this could mean the universe has been recycling itself all along. Matter swallowed by black holes in one corner of spacetime might be reborn elsewhere, fueling new stars, galaxies, or even entire universes. It's a vision of cosmic sustainability, where nothing is ever truly wasted, just repurposed on an unimaginable scale. Some theorists go further, suggesting these quantum tunnels could explain mysterious high-energy events in space, like gamma-ray bursts or fast radio bursts. Could these be the distant flashes of white holes coughing up matter from another time and place? Of course, the biggest question remains: how do we prove it? Detecting a white hole's telltale outburst would be like finding a needle in a universe-sized haystack. But if we ever do, it wouldn't just confirm a wild hypothesis. It would rewrite the rules of reality itself, revealing a universe far more dynamic, interconnected, and alive than we ever dared to dream. Now let's turn to one of the most tantalizing possibilities. What if white holes aren't just cosmic anomalies, but the hidden architects of the universe's greatest mystery? Hypothesis 3 throws open the door to a radical idea. White holes could be the invisible factories churning out dark matter, the elusive substance that makes up most of the universe's mass yet refuses to interact with light. Think about it: while black holes pull everything in, their white hole counterparts could be spewing out particles we've never seen, flooding the cosmos with the very material that holds galaxies together. For decades, scientists have known dark matter exists because of its gravitational grip. It bends light, warps spacetime, and keeps stars from flying apart in their galaxies. But despite its overwhelming presence, no one ever directly detected it. That's where white holes could rewrite the story. If these objects eject exotic particles, ones that don't reflect, absorb, or emit light, they could be the missing source of dark matter's ghostly influence. Picture a hidden cosmic conveyor belt. Black holes swallow ordinary matter, while white holes release its shadowy counterpart, creating an invisible scaffolding that shapes the universe. And the plot thickens. This hypothesis could also solve another puzzle: dark energy. The force driving the universe's accelerating expansion remains just as mysterious as dark matter. But if white holes don't just eject matter, but also flood space with repulsive energy, they might be the engine behind this runaway expansion. It's a two-for-one cosmic deal, one phenomenon explaining two of science's biggest headaches. Some models even suggest that white holes could be leaking energy from other dimensions or parallel universes, making them cosmic portals bridging realities we can't yet perceive. Critics argue that this idea stretches physics to its limits. After all, no one ever observed a white hole's dark matter factory in action. But supporters counter that absence of evidence isn't evidence of absence. If white holes are as rare as they are fleeting, their dark matter output could be subtle, blending into the background of the universe. Future telescopes tuned to catch exotic particle signatures or gravitational wave anomalies might finally spot their handiwork. Imagine the implications. If white holes truly are the source of dark matter, they're not just oddities, they're the universe's silent puppeteers, shaping everything from the smallest galaxy to the largest cosmic web. Finding one wouldn't just fill a gap in our theories, it would reveal the hidden machinery behind reality itself. And that's a discovery worth waiting for. What if the key to understanding white holes isn't hidden in space, but in time itself? Hypothesis 4 flips the script on everything we thought we knew, proposing that white holes might not be separate objects at all, but black holes playing the universe's greatest rewind. Picture a black hole's crushing grip not as a one-way journey, but as a cosmic film reel running backward. Matter isn't swallowed, but expelled, not vanishing, but erupting. This isn't just poetic imagery. It's a theory grounded in the cold, hard math of general relativity, where the equations describing black holes can just as easily describe their opposites if you reverse the arrow of time. The idea hinges on a profound symmetry in physics. At their core, the laws governing the universe don't actually care which direction time flows. A black hole's singularity, where gravity becomes infinite and spacetime curves beyond recognition, could mathematically transform into a white hole's outburst if time ran in reverse. Imagine pressing play on a video of a black hole devouring a star, then hitting rewind. The star would reassemble, the explosion would reverse, and suddenly you're watching a white hole in action. To an outside observer, these two scenarios could be indistinguishable from reality. But here, where it gets surreal. If white holes are truly black holes in reverse, they might not just defy gravity, they could defy causality itself. Events that should unfold in strict order, cause before effect, past before future, might blur at the edges of a white hole. Some theorists speculate these objects could be portals to alternate timelines where the usual rules don't apply. A particle ejected from a white hole might not just be emerging from nowhere. It could be arriving from a future that hasn't happened yet, or a parallel universe where time flows backward. This raises existential questions. If time can reverse on cosmic scales, does that mean the universe has a built-in undo button? Could white holes be evidence of a deeper, cyclical nature to reality, where beginnings and endings are illusions? The implications ripple through philosophy as much as physics, challenging our most basic assumptions about free will, destiny, and the very nature of existence. Yet for all its elegance, the theory faces fierce skepticism. Time's arrow, the unidirectional flow from past to future, is baked into our experience of reality. Entropy increases, memories form, and eggs don't unscramble themselves. If white holes truly reverse time, why don't we see their effects more clearly? Supporters counter that these objects might be extraordinarily rare or short-lived, flickering into existence just long enough to spit out a burst of energy before collapsing back into the fabric of spacetime. Others suggest they could be hiding in plain sight, masquerading as unexplained cosmic explosions or gamma-ray bursts. The search for answers might lie in the quirks of quantum mechanics. At microscopic scales, particles already behave as if time isn't strictly linear, with effects sometimes seeming to precede causes. If this quantum weirdness scales up to white holes, it could mean these objects are the universe's way of stitching together timelines we can't yet perceive. Future experiments probing the nature of time or hunting for exotic gravitational waves might finally reveal whether this hypothesis is a mathematical curiosity or a revolutionary clue to the cosmos's deepest secrets. One thing's certain: if white holes are black holes in reverse, the universe is far stranger than we ever imagined. Not just a stage for matter and energy, but a labyrinth of time itself, where the past and future might not be fixed, but fluid, interchangeable, and full of surprises. The universe at its smallest scale is anything but calm. It's a seething, bubbling ocean of chaos known as quantum foam, where spacetime itself churns with unimaginable energy. In this frenzied dance of virtual particles, reality flickers in and out of existence so quickly that even the laws of physics seem to blur. And hidden within this subatomic storm, some theorists believe, could be the seeds of white holes, tiny, fleeting bursts of repulsive gravity that wink into existence for mere fractions of a second before vanishing back into the void. This isn't just wild speculation. Quantum mechanics tells us that empty space is anything but empty. Particles and antiparticles constantly pop into being, borrowing energy from the universe before annihilating each other in a flash. Under the right conditions, these quantum fluctuations might twist spacetime so violently that they create microscopic white holes, cosmic hiccups where gravity reverses direction and matter is spat outward instead of sucked in. Picture a boiling pot of water with bubbles forming and bursting at the surface. Except here, the bubbles are entire pockets of inverted physics, erupting across the fabric of reality itself. The implications are staggering. If white holes really do emerge from quantum foam, they could be everywhere, woven into the very structure of spacetime. Too small and short-lived to observe directly, their collective influence might still leave traces in the behavior of particles or the subtle warping of light. Some scientists speculate that these transient white holes could even explain dark energy, the mysterious force accelerating the universe's expansion. Imagine trillions upon trillions of these minuscule eruptions, each one pushing spacetime outward like an invisible cosmic pressure. But how could we ever detect something so ephemeral? Current technology is light years away from observing phenomena this brief and tiny, but future breakthroughs in quantum gravity research might offer a glimpse. Experiments probing scale physics, the realm where spacetime itself becomes granular, could uncover indirect evidence, like anomalies in particle collisions or unexpected ripples in gravitational waves. If we ever crack that code, it wouldn't just confirm white holes. It would reveal a universe far more dynamic and alive than we ever imagined, where even the vacuum of space teems with hidden structures and energies. And here's the most mind-bending part. If white holes are constantly bubbling up in quantum foam, they might not just be shaping the cosmos. They could be rewriting the rules of existence itself. Each one might represent a tiny reset button, a momentary defiance of entropy where order briefly triumphs over chaos. In a sense, the universe could be endlessly regenerating itself at the smallest scales, with white holes as its unsung architects. That's the kind of revelation that doesn't just change textbooks, it changes how we see reality. What if the secret to crossing the universe in the blink of an eye has been hiding in plain sight, not in futuristic warp drives, but in the bizarre physics of white holes? Hypothesis 6 takes us into the realm of wormholes, those legendary cosmic tunnels that could connect distant corners of spacetime in an instant. But here's the twist. For a wormhole to work, it might need a white hole as its exit door, a dazzling burst of matter and energy marking the end of the journey. Equations hinted at this possibility nearly a century ago with the concept of bridges. These theoretical structures link the crushing depths of a black hole to the explosive output of a white hole, forming a bridge through the fabric of spacetime itself. Picture it like a cosmic subway. Matter enters through the black hole's relentless pull, hurdles through the wormhole's twisted geometry, and gets spat out the other side by a white hole's defiant push. The math checks out, but the reality would be stranger than fiction. For interstellar travelers, this could be the ultimate shortcut. Instead of spending crossing the void between stars, a ship could plunge into a black hole and emerge light years away in moments, at least in theory. The catch: surviving the trip would require navigating conditions so extreme they border on impossible. The gravitational forces near a black hole's singularity could shred matter into its fundamental particles, while the white hole's violent outburst might scatter anything emerging in a chaotic spray of energy. It's like trying to ride a tornado through a keyhole and hoping to land gracefully on the other side. Yet the allure is undeniable. If traversable wormholes exist, they wouldn't just revolutionize space travel, they'd rewrite our understanding of the cosmos. Galaxies too distant to reach in a human lifetime could suddenly become neighbors. Civilizations separated by billions of light years might share knowledge, resources, or even cultures. The universe would shrink from a vast expanse to a tightly knit web of interconnected points. But there's a darker side to this hypothesis. Wormholes sustained by white holes might be inherently unstable, snapping shut the moment anything tries to pass through. The energy required to keep them open could defy the laws of physics as we know them, demanding exotic matter with negative energy density, a substance that may not even exist. And then there's the time paradox problem. If wormholes connect not just space but time, traversing one could mean arriving before you left, unraveling causality in ways that make even seasoned physicists shudder. Despite the challenges, the search for these cosmic shortcuts continues. Some theorists suggest that microscopic wormholes might flicker in and out of existence within quantum foam, too small and fleeting to be useful. Others speculate that advanced civilizations, if they exist, could have already mastered the technology to stabilize them, leaving behind detectable signatures like anomalous gamma-ray bursts or distorted gravitational waves. Whether wormholes remain fantasy or future fact, one thing is clear. If white holes truly are their exits, the universe is far more interconnected than we ever dreamed. And that's a possibility worth exploring, no matter how wild the journey may be. Could our universe be just one page in an infinite cosmic library, with white holes serving as the passages between chapters? Hypothesis 7 ventures into the mind-bending territory of the multiverse, proposing that these elusive objects might not just defy physics, they could defy reality itself by acting as gateways to parallel dimensions. Imagine a white hole not as the end of a cosmic journey, but as a doorway, ejecting matter and energy not into our universe, but into an entirely different one. This isn't just speculative fiction. It's a possibility grounded in the cutting-edge mathematics of string theory and brane cosmology, where our universe is just one brain floating in a higher dimensional space, like a sheet of paper suspended in a vast, unseen ocean. The idea hinges on a radical reimagining of white holes' behavior. Instead of spewing matter back into our cosmos, they might funnel it into adjacent branes, parallel universes separated by dimensions we can't perceive. Picture a bubble floating in a foam of other bubbles, each one a self-contained reality with its own laws of physics. A white hole in our bubble could be the point where matter slips through the film into another, explaining why we've never observed one directly. They might not be hiding, they could simply be redirecting their output somewhere else entirely. This theory dovetails with one of the most profound mysteries in physics, why our universe seems so finely tuned for life. If white holes are constantly shuttling matter and energy into other dimensions, it could mean our cosmos is just one thread in a grand tapestry of universes, each with different constants and physical laws. Some might collapse instantly, others could be barren voids. But in a few like ours, the conditions might align perfectly for stars, planets, and life to emerge. It's a cosmic lottery, and white holes could be the unseen hands shuffling the tickets. The implications stretch beyond mere curiosity. If white holes bridge universes, they might also carry echoes of those other realities. Strange particles or energy signatures with no clear origin in our universe could be refugees from another brain, hints of a greater multiverse just out of reach. Some researchers speculate that high-energy cosmic rays or unexplained quantum anomalies might be traces of this traffic. Detecting them could be our first glimpse into a reality far larger and stranger than we ever imagined. Yet the biggest hurdle remains. How do you test a hypothesis about something that, by definition, exists beyond our observable universe? Critics argue this idea skirts the edge of pseudoscience, but supporters counter that the math holds up even if the technology to prove it doesn't yet exist. Future advances in particle physics or gravitational wave astronomy might uncover subtle fingerprints of brain interactions, like ripples in spacetime that can't be explained by local events. Others suggest that if a white hole ever did open a crack between dimensions, it might leave behind a unique signature, a burst of energy with properties that defy known physics, like a cosmic hello from another reality. Whether this hypothesis is a stroke of genius or a step too far into the unknown, one thing's certain. It forces us to confront the humbling possibility that our universe is far from alone. And if white holes are the thread stitching these realities together, they're not just cosmic oddities. They're the keys to unlocking the greatest mystery of all. What lies beyond the edges of everything we know? What if the universe has a cosmic rulebook ensuring its most dangerous secrets stay locked away? That's the essence of the cosmic censorship conjecture, a daring idea proposing that singularities, the infinitely dense, lawless cores of black holes, must always be hidden behind event horizons, veiled from view like monsters in the shadows. But white holes might be the ultimate rule breakers, tearing off that cosmic veil to expose naked singularities to the universe. Picture a breach in reality itself, a point where gravity becomes infinite, time loses meaning, and the equations physicists rely on dissolve into chaos. This isn't just theoretical, it's where the foundations of physics could rise or fall. The controversy boils down to predictability. In this universe, physics is a clockwork symphony. Matter moves, energy flows, and the future can, in theory, be calculated from the present. But a naked singularity throws a wrench into that machinery. Without an event horizon to contain it, its infinite distortions would ripple outward, warping spacetime in unpredictable ways. Stars might flicker like candles in a hurricane, or particles could blink in and out of existence at random. It's the scientific equivalent of opening Pandora's box. Once the singularity is exposed, there's no telling what rules apply, or if any do at all. Yet for some theorists, that's exactly why white holes matter. If they truly unveil naked singularities, these objects could be less about destruction and more about revelation, forcing us to confront the limits of general relativity and quantum mechanics. The violent physics at a singularity's heart might hold clues to a deeper theory, one that unifies gravity and quantum forces into a single framework. Imagine a white hole as a cosmic lab, conducting experiments in extreme gravity that no particle collider could ever replicate. The data would be messy, even terrifying, but it might be the key to unlocking the next revolution in physics. Opponents counter that naked singularities aren't just disruptive, they're impossible. The universe, they argue, simply wouldn't allow such chaos to exist. Mathematical models suggest that forming a naked singularity would require conditions so precise they border on absurd, like balancing a pencil on its tip in a hurricane. Even if one did form, quantum effects or hidden dimensions might step in to reclothe it, restoring order before the damage spreads. It's a cosmic immune response, protecting reality from its own worst excesses. But what if we've been looking at this backward? Instead of white holes breaking the rules, maybe they're revealing rules we never knew existed. Some cutting-edge theories propose that singularities aren't infinitely dense after all, that quantum gravity steps in to prevent the infinite, replacing the singularity with something stranger but less destructive. A white hole's core might be a knot of spacetime threads, a quantum bounce, or even a portal to something beyond our current math. In this light, cosmic censorship isn't violated, it's upgraded, with white holes acting as cosmic editors, redacting the old laws to make room for new ones. The stakes couldn't be higher. If naked singularities exist, they'd challenge not just our equations, but our very understanding of cause and effect. Yet if they don't, white holes might be even weirder than we thought, not cosmic rebels, but cosmic diplomats, negotiating the boundary between the known and the unknowable. The answer could lie in the faint echoes of gravitational waves or the cryptic signals of distant quasars, hints of physics pushed to its breaking point. One thing's certain, the universe hates to be predictable, and white holes might be its wildest plot twist yet. String theory has always danced on the edge of science fiction, a framework where the universe isn't just made of particles and forces, but of tiny, vibrating strings humming in hidden dimensions. Most of us are familiar with the 4 dimensions of spacetime: length, width, height, and time. But what if there are more, curled up so tightly we've never noticed them? Hypothesis 9 takes this mind-bending idea and runs with it, suggesting that white holes might not just be cosmic anomalies in our universe. They could be the fallout from collisions in dimensions we can't even see. Picture our universe as a single sheet of paper floating in a higher dimensional space, a brain in string theory parlance. Now imagine another brain drifting nearby, another universe with its own laws, its own history. If these brains collide or brush against each other, the energy released could be staggering, enough to tear open a rupture in spacetime itself. And here, where white holes enter the story, these collisions might not just create explosions within a universe, but portals between them, funneling energy from higher dimensions into ours in a violent burst. What we perceive as a white hole could just be the 3-dimensional shadow of a far more complex, multi-dimensional event, like watching a flat silhouette of a fireworks display and missing the full spectacle. This isn't just wild conjecture. The math of string theory allows for scenarios where brain collisions transfer energy asymmetrically, leaving behind remnants that behave exactly like white holes, objects that defy local physics because their origins lie outside local physics. Some models even suggest that the Big Bang itself could have been triggered by such a collision, meaning our entire universe might owe its existence to a higher dimensional white hole event. It's a cosmic Russian nesting doll, with each layer revealing a deeper mystery. But how would we ever detect something like this? If white holes are higher dimensional artifacts, their signatures might be hiding in plain sight. Unexplained bursts of cosmic rays, anomalies in the cosmic microwave background, or even peculiar gravitational wave patterns could be clues, subtle echoes of dimensions beyond our perception. Future experiments probing the fabric of spacetime at unimaginably small scales, like next-generation particle colliders or quantum gravity sensors, might finally catch a glimpse of these hidden dimensions. And if they do, it wouldn't just confirm white holes. It would revolutionize our understanding of reality itself, proving that what we call the universe is just one slice of a far grander, stranger whole. The implications stretch beyond physics into philosophy. If white holes are windows into higher dimensions, they challenge the very notion of what's real. Our 4-dimensional world might be a pale reflection of a richer, more complex cosmos, with white holes as fleeting glimpses behind the curtain. It's a humbling thought, one that turns these enigmatic objects from cosmic oddities into messengers, carrying secrets from realms we're only beginning to imagine. Black holes might be the universe's ultimate shredders, tearing matter apart beyond recognition. But what if nothing is ever truly gone? Hypothesis 10 flips the script, proposing that white holes could be the cosmos's fail-safe mechanism, meticulously preserving and reconstructing quantum information like celestial librarians cataloging every atom's story. At the heart of this idea lies one of physics' most sacred principles: information can never be destroyed. Yet when black holes evaporate over eons, seemingly taking secrets with them, where does that data go? The answer might lie in their mysterious counterparts, white holes, acting as cosmic archives that eventually spit the information back out, perfectly intact. Think of it like a cosmic game of hide-and-seek. When a black hole swallows a star, every particle's quantum state, its spin, charge, and position is scrambled beyond measure. For decades, physicists wrestled with the nightmare scenario that this information might vanish forever, violating quantum mechanics' core rules. But if white holes exist as the universe's undo button, they could be stitching that data back together, piece by piece, in an eruption of resurrected quantum states. It's as if the cosmos has a built-in backup system, ensuring no detail, no matter how small, is ever lost to the void. This isn't just poetic symmetry, it's a solution with teeth. The math behind quantum gravity suggests that black holes don't just trap information, they encode it in their event horizons, imprinting data like a hologram on their surfaces. As the black hole decays via Hawking radiation, that information doesn't disappear. It's transferred, waiting for the right conditions to re-emerge. Enter the white hole, a theoretical endpoint where spacetime itself reboots, unpacking that compressed data in a burst of perfectly reconstructed particles. Picture a crumpled letter smoothed back to legibility, its words preserved against all odds. The implications ripple far beyond theory. If white holes are quantum correctors, they might explain why the universe feels so finely tuned. Random fluctuations, cosmic accidents, or even entropy itself could be constantly balanced by these hidden mechanisms, quietly ensuring stability amid chaos. Some researchers even speculate that this process could underpin dark energy or the universe's accelerating expansion, like a cosmic exhale after the black holes inhale. But the real magic lies in the timing. Quantum resurrection wouldn't happen on human scales. The process could take billions of years, unfolding only after a black hole's evaporation is complete. To witness it, we'd need patience beyond comprehension, or a way to detect the faint echoes of information leaking back into spacetime. Future quantum gravity experiments or advanced gravitational wave observatories might catch whispers of this process, like eavesdropping on the universe's self-repair sequence. Critics argue that this hypothesis leans too heavily on unproven quantum gravity models. Yet supporters counter that it's the most elegant solution to one of physics' greatest paradoxes, a way to reconcile the brutal chaos of black holes with the delicate precision of quantum mechanics. If true, white holes aren't just cosmic oddities. They're the universe's silent guardians, ensuring that every bit of information, from the spin of an electron to the light of a dying star, gets a second act. And that changes everything. The holographic principle sounds like something straight out of a sci-fi movie, but it's one of the most serious ideas in theoretical physics today. At its core, it suggests that our three-dimensional universe, with all its depth and complexity, might actually be a projection of information stored on a two-dimensional surface at the very edge of reality. Think of it like a cosmic version of a hologram. The image you see has volume and shape, but all the data creating it is encoded on a flat two-dimensional sheet. Now here, where white holes come in, what if these mysterious objects aren't just cosmic anomalies, but the literal pixels in this grand cosmic display, flickering to life as they emit the universe's hidden code? This idea stretches back to the study of black holes, where physicists discovered something bizarre. The amount of information a black hole can hold isn't proportional to its volume, it's tied to the surface area of its event horizon. That's like saying the data stored in a computer isn't in its hard drive's bulk, but etched onto its outer shell. If black holes obey this rule, why wouldn't their counterparts? White holes in this framework could be the universe's way of rendering that stored information back into existence, translating two-dimensional data into three-dimensional reality. Picture them as cosmic projectors, taking the universe's underlying code and casting it into the space we experience. The implications are staggering. If white holes are tied to the holographic principle, they're not just objects, they're processes, fundamental to how spacetime itself functions. Every time one erupts, it might not just be spewing matter and energy. It could be updating the cosmic display, refreshing reality like a pixel on a screen. Some theorists even speculate that this could explain why white holes seem so rare or short-lived. They might not be enduring structures, but fleeting events, brief flashes where the universe's hidden data bubbles to the surface before fading back into the background code. But how would we ever test such a radical idea? The holographic principle is already a challenge to observe directly, let alone its connection to white holes. Yet there are hints. If white holes truly are tied to information at the universe's edge, their outbursts might carry subtle fingerprints, patterns in the particles or energy they emit that mirror the underlying two-dimensional data. Future telescopes or quantum gravity experiments might detect these signatures, like finding a watermark hidden in the fabric of spacetime. Even wilder, this hypothesis could redefine what we consider real. If white holes are pixels in a cosmic hologram, then everything we see, touch, and experience might just be the universe's way of interpreting data we can't directly perceive. It's a humbling thought. The stars, the planets, even our own existence might be projections of something far more fundamental, with white holes as the brief moments where the veil slips and the universe's true nature shines through. Dark energy is the universe's greatest unsolved riddle, an invisible force stretching space itself apart, pushing galaxies away from each other faster and faster with no clear source. But what if the answer has been hiding in plain sight, masquerading as one of cosmology's most enigmatic objects? Hypothesis 12 throws white holes into the spotlight as potential dark energy engines, their explosive outward momentum acting as cosmic accelerators on the grandest scale imaginable. Think of it like this. If black holes are the universe's vacuum cleaners relentlessly sucking matter inward, white holes would be their opposites, cosmic leaf blowers spraying energy and particles outward with unstoppable force. Now imagine countless white holes scattered across the cosmos, each one contributing a tiny push to the fabric of spacetime. Add them all up, and you might just have the recipe for dark energy's relentless expansion. It's a radical idea, but the math hints at something profound. When physicists model white holes in the equations of general relativity, their repulsive gravity doesn't just defy black hole behavior. It mirrors the kind of outward pressure we attribute to dark energy. The beauty of this hypothesis lies in its simplicity. For decades, dark energy has been a placeholder, a label slapped onto an effect we don't understand. But if white holes are real, they could turn this abstract concept into something concrete, a population of exotic objects actively driving the universe's acceleration. Instead of invoking mysterious quantum fields or unseen dimensions, we'd be looking at a phenomenon rooted in the same physics that governs black holes, just flipped inside out. Critics are quick to point out the hurdles. If white holes are fueling dark energy, why haven't we detected their individual contributions? The answer might lie in scale and distribution. A single white hole's outburst would be fleeting and localized, but if they're woven evenly throughout spacetime, perhaps as remnants of primordial quantum fluctuations, their combined effect could be subtle, uniform, and everywhere at once. Like invisible threads tugging at the cosmos from all directions, their collective push would look eerily like the smooth, omnipresent force we call dark energy. There's another tantalizing possibility. White holes might not just explain dark energy's existence, they could clarify why its strength appears so finely tuned. If these objects are tied to the universe's earliest moments, their numbers and energy output might be locked into fundamental constants, creating the precise balance needed for galaxies to form without collapsing or tearing apart too quickly. It's a cosmic Goldilocks scenario, where white holes act as the universe's built-in thermostat, regulating expansion to just the right rate for complexity and life to emerge. Of course, proving this would require catching white holes in the act. Astronomers might search for anomalies in the large-scale structure of the universe, patterns in galaxy distribution, or subtle ripples in the cosmic microwave background that hint at white holes' cumulative influence. Others suggest that if white holes are unevenly distributed, their dark energy footprint could leave detectable voids or flows in intergalactic space. Whether this hypothesis holds up or not, it forces us to confront a humbling truth. The universe's greatest mysteries might not demand entirely new physics, just a fresh perspective on the physics we already have. And if white holes really are the hidden hands behind dark energy, they're not just cosmic oddities, they're the architects of reality's fate, silently shaping everything from the smallest atoms to the largest superclusters. That's a discovery worth rewriting the textbooks for. Neutron-star collisions are some of the most cataclysmic events in the universe. Two city-sized remnants of dead stars, each more massive than our sun, spiraling toward each other at nearly the speed of light before smashing together in a blaze of gamma rays and gravitational waves. But hidden within that chaos might be something even stranger, the birth of a white hole. Hypothesis 13 flips the script on these cosmic crashes, suggesting that under the right conditions, neutron-star mergers might not always form black holes. They could instead forge white holes, erupting with enough force to fling matter across the cosmos at near-light speed. The idea hinges on the extreme physics at play during these collisions. When neutron stars merge, their combined density reaches levels so absurd that even the laws of quantum mechanics start to falter. Under normal circumstances, this collapse forms a black hole, but some theoretical models reveal an alternative. If the merged star's core reaches a critical threshold of spin or energy, the collapse might trigger a quantum rebound, like a spring compressed to its limit before suddenly snapping back. Instead of vanishing behind an event horizon, the matter could explode outward, creating a white hole's signature outburst. Picture a cosmic pressure cooker that doesn't just release steam, it blows its lid clean off, scattering stellar debris in a dazzling, high-speed spray. This wouldn't be a gentle process. The newborn white hole would unleash energy equivalent to a supernova, ejecting jets of matter so fast they'd rival the speed of light. These jets, packed with heavy elements like gold and platinum forged in the collision, could seed galaxies with the building blocks of planets and life. It's a twist on the classic tale of neutron-star mergers. Instead of creating a silent, invisible black hole, they might occasionally give birth to a brilliant, universe-altering flare. The real smoking gun would be catching one of these events in action. Gravitational wave detectors like LIGO and Virgo have already spotted neutron-star collisions, but so far, every confirmed merger has ended with a black hole. Yet theorists argue we might simply be missing the white hole signatures. Unlike black holes, which swallow light whole, a white hole's explosion would be visible. A sudden, intense flash of gamma rays followed by an unusual afterglow, like a firework lingering in the sky. Some astronomers are already sifting through old data, searching for unexplained bursts that match this profile. There's another clue hidden in the debris. If a neutron-star collision produces a white hole, the ejected matter wouldn't just be any random mix of particles. It would carry a distinct fingerprint, a specific ratio of heavy elements unlike anything a black hole could produce. Future telescopes capable of analyzing the chemical makeup of distant cosmic explosions might spot this telltale signature, turning a theoretical possibility into hard evidence. Of course, skeptics point out the obvious hurdle. If white holes form this way, why haven't we definitively seen one? The answer might lie in their rarity. Only a tiny fraction of neutron-star mergers might have just the right conditions, the perfect spin, the exact mass to trigger a white hole instead of a black hole. It's like searching for a needle in a haystack, except the haystack is the entire observable universe, and the needle only glows for a split second. But if we ever do find one, the implications would be staggering. Not only would it confirm white holes as real astrophysical objects, but it would reveal an entirely new channel for their formation, one that ties them to some of the most energetic events in nature. It would also force us to rethink the life cycle of neutron stars, adding a spectacular twist to their already dramatic story. And perhaps most tantalizing of all, it would suggest that the universe has more than one way to defy gravity's pull, rewriting the rules of stellar evolution in the process. For now, the hunt continues. Every new neutron-star collision detected is a potential clue, a chance to spot the universe's most elusive rebels in action. And if the models are right, the proof might already be out there, hidden in the light of an ancient explosion, waiting for us to connect the dots. What if the universe has been quietly preserving its own history, not in dusty archives or ancient fossils, but in the explosive outbursts of white holes? Hypothesis 14 paints these enigmatic objects as cosmic time capsules, vaults hurling pristine fragments of the past into our present, untouched by billions of years of cosmic evolution. Unlike black holes that lock away secrets forever, white holes might be the universe's way of unpacking its deepest memories, offering astronomers a direct line to epochs long vanished. Picture a white hole not just as a fountain of matter, but as a messenger from the dawn of time. Every particle it ejects could carry imprints of conditions from an era when galaxies were just sparks in the darkness. The hydrogen atoms it sprays might be older than the Milky Way, their quantum states frozen in the exact configuration they held moments after the Big Bang. For scientists, this would be like discovering a library where every book is written in the universe's original language, a chance to decode the raw physics of creation itself. The key lies in the peculiar nature of white hole emissions. Because these objects theoretically reject all incoming matter, anything they expel has never been contaminated by later cosmic events. It's the difference between studying a dinosaur bone fossilized in rock and holding a living cell from the Jurassic period. A white hole's outburst could deliver pristine samples of primordial plasma, unaltered by stars, supernovae, or the turbulent magnetic fields that scramble most ancient signals. Even the cosmic microwave background, our current window into the early universe, is a faded, processed remnant. White holes might offer the unfiltered version. But how would we read these cosmic artifacts? Advanced spectrographs could analyze the elemental composition and quantum signatures of particles from white hole eruptions, searching for anomalies that betray their age. For instance, ratios of isotopes that only existed in the universe's first minutes, or patterns in particle spin that reflect the extreme densities of the primordial fireball. Some theorists even suggest that certain high-energy neutrinos or cosmic rays, particles that now arrive with no clear origin, might actually be white hole postcards from the past, their energy levels matching predictions for emissions from the early cosmos. The potential discoveries are staggering. White holes could settle debates about inflation, the universe's explosive growth spurt, by revealing whether space really stretched as dramatically as models suggest. They might expose hidden properties of dark matter or even uncover evidence of universes that existed before our own. Every burst would be a time-stamped snapshot, a piece of the cosmic puzzle we've been missing. Yet the challenges are just as profound. If white holes are rare or fleeting, catching one in the act would demand unprecedented coordination between telescopes and particle detectors. Their emissions might blend with more mundane astrophysical events, requiring AI-driven algorithms to spot the subtle differences. And there's the existential question. If a white hole's matter is truly from the past, does that mean it's breaking causality? Or is the universe simply recycling its history in ways we're only beginning to grasp? For now, the hunt remains speculative, but the stakes couldn't be higher. If white holes are indeed time capsules, they're not just curiosities. They're invitations to rewrite the story of everything, one ancient particle at a time. And that's a discovery worth waiting for, no matter how long it takes. The Fermi Paradox is one of the most haunting questions in science. If the universe is so vast and ancient, why does it feel so empty? With trillions of planets, where is everyone? Hypothesis 15 offers a radical solution. What if the answer has been staring us in the face, hidden in the physics of white holes? If advanced civilizations exist, they might not be broadcasting radio signals or building megastructures we can spot. Instead, they could be harnessing white holes, objects so alien to our understanding that their technology would be invisible to our telescopes, rewriting the rules of the cosmic hide-and-seek we've been playing for decades. Think about how humanity uses energy. We started with fire, then coal, then nuclear fission, each leap unlocking exponentially more power. Now imagine a civilization millions of years ahead of us. They wouldn't be mining asteroids or building spheres, they'd be tapping into the universe's most extreme energy sources. A white hole's violent outbursts release more energy than 1,000 supernovae, making them the ultimate power plants. An advanced society might not just observe these objects. They could stabilize them, control them, even trigger their eruptions on demand. The energy output would dwarf anything we consider possible, fueling technologies so advanced they'd look like magic, or be entirely undetectable to our instruments. This reshapes the Fermi Paradox entirely. The Great Silence isn't proof we're alone, it's proof we're searching for the wrong things. White hole-based technology wouldn't leave the traditional signatures we associate with alien civilizations. No radio waves, no heat signatures, no visible megastructures. Instead, their presence might be hidden in the subtle anomalies of high-energy astrophysics. Unexplained gamma-ray bursts with odd timing, particles accelerating to impossible speeds, or gravitational waves that don't match any known cosmic event. We could be surrounded by interstellar traffic, even intergalactic civilizations, and never know because their infrastructure operates on physics we haven't yet uncovered. There's another layer to this idea. White holes might not just power advanced societies, they could be their preferred method of travel. If traversable wormholes exist, as some models suggest, white holes would be the natural exit points, creating a network of cosmic highways. A civilization mastering this technology wouldn't need starships. They'd step through spacetime itself, appearing and disappearing without a trace. To us, their movements would look like random astrophysical phenomena, if we noticed them at all. The universe might be teeming with life, but we're like ants on a highway, oblivious to the cars zooming past because we lack the senses to perceive them. Critics argue this is a convenient excuse for the lack of evidence, a way to explain away the silence without proof. But supporters counter that it's not about making excuses, it's about recognizing the limits of our current tools and theories. 100 years ago, we wouldn't have been able to detect neutrinos or gravitational waves. Who knows what signatures of white hole engineering we're missing now? Future observatories like next-gen gravitational wave detectors or quantum entanglement telescopes might finally catch the whispers of these technologies. Until then, the paradox remains open, not because the aliens aren't there, but because we've been searching for footprints in the wrong dimension. The implications are humbling. If white holes are the key to the Fermi Paradox, humanity isn't just late to the cosmic party. We might be standing outside the door, knocking quietly while the real celebration happens in realms we can't yet see. It's a reminder that the universe is under no obligation to make itself obvious to us. And that's the most exciting possibility of all. The greatest discoveries aren't just about finding answers. They're about realizing how much bigger the questions really are. Quantum mechanics has already shown us that empty space isn't empty at all. It's a seething, bubbling cauldron where particles flicker in and out of existence in a dance as old as time itself. These quantum fluctuations, governed by uncertainty principle, allow energy to briefly manifest as matter before vanishing back into the void. But what if white holes don't just participate in this cosmic ballet? What if they hijack it, amplifying these fleeting flickers into full-fledged eruptions of reality? Hypothesis 16 takes this wild possibility seriously, suggesting that white holes could act as quantum fluctuation amplifiers, transforming the universe's background static into a symphony of creation. At the heart of this idea lies a paradox that would make even pause: the apparent violation of energy conservation. Physics has always held that energy can neither be created nor destroyed. Yet if white holes magnify quantum fluctuations, they might effectively pull matter from nothingness, like a magician conjuring rabbits from an empty hat. Imagine a white hole's immense gravitational repulsion not just ejecting trapped matter, but stretching the fabric of spacetime so violently that it tears open gaps in reality itself. Within those gaps, virtual particles, usually doomed to annihilate each other instantly, could be ripped apart before they can recombine, their fleeting existence made permanent by the white hole's explosive energy. One half of the particle pair gets sucked back into the quantum foam, while the other is hurled outward, now a real, tangible piece of the universe. It's cosmic alchemy, turning the ephemeral into the eternal. This isn't just theoretical sleight of hand. The math of quantum field theory and curved spacetime, a framework blending relativity with quantum mechanics, hints that extreme gravitational environments can indeed amplify fluctuations. Near a black hole's event horizon, we see this as Hawking radiation, where particle pairs are split, allowing one to escape while the other falls inward. A white hole's repulsive gravity could operate in reverse, acting like a cosmic particle accelerator cranked to its maximum setting. Instead of gently pulling pairs apart, it might blast them into existence with enough force to overcome their natural tendency to vanish. The result, a fountain of particles that, to any observer, would seem to appear from nowhere. The implications rewrite the rules of cosmology. If white holes generate matter X, they could be the hidden engines behind the universe's structure, seeding galaxies with the raw material for stars, planets, and life. Mysterious pockets of unexplained matter or regions of space with unusual energy densities might not be anomalies. They could be the fingerprints of white holes quietly manufacturing reality. Some theorists even speculate that this process could explain dark matter's origin, with white holes producing exotic particles that don't interact with light but still shape the cosmos through gravity. Yet the controversy is undeniable. Energy conservation isn't just a guideline, it's the bedrock of physics. If white holes truly break this rule, even locally, it would demand a radical rethinking of our most fundamental theories. Supporters argue that the energy might not be created but borrowed, with the white hole's gravitational field acting as a cosmic loan shark, deferring the debt to some deeper quantum accounting system. Others suggest that the universe's total energy might still balance if the white hole's outburst is offset by negative energy elsewhere, perhaps in the form of twisted spacetime or hidden dimensions. The search for evidence is already. Astronomers scour the skies for unexplained particle jets or regions where matter seems to appear without a clear source. Quantum physicists simulate extreme gravitational environments in supercomputers, hunting for signs of fluctuation amplification. And if the hypothesis holds, the payoff would be staggering. Proof that the universe isn't just recycling matter, but actively creating it, with white holes as its clandestine workshops. Whether this idea is a stroke of genius or a step too far into the speculative, one thing is certain. It forces us to confront the unsettling possibility that reality's rulebook might have pages we haven't even glimpsed yet. And if white holes are truly matter factories, they're not just cosmic oddities. They're the universe's way of reminding us that nothing, not even the vacuum of space, is ever truly empty. Plasma cosmology has always been the rebel of astrophysics, a framework that tosses out black holes, dark matter, and even the Big Bang in favor of a universe woven from electric currents and magnetized plasma. To mainstream scientists, it's a fringe idea. But here, where things get interesting, what if this renegade theory isn't just tearing down established concepts, but secretly making room for something even wilder? Hypothesis 17 flips the script, suggesting that while plasma cosmology might reject black holes, it could have a surprising place for their polar opposites, white holes, rebranded as the engines behind some of the universe's most powerful jets. Picture the cosmos not as a static arena of gravity-dominated objects, but as a dynamic electrical circuit, where filaments of plasma stretch across millions of light years, carrying currents strong enough to sculpt galaxies. In this view, black holes are unnecessary, their gravitational pull replaced by the twisting forces of electromagnetism. But cosmic jets, those narrow beams of matter screaming outward at nearly light speed from galactic cores, still need an explanation. Enter white holes, reimagined not as space-time singularities, but as plasma-filled vortices. Instead of a black hole's infinite gravity well, these objects would be colossal plasma focusers, concentrating electromagnetic energy until it erupts in a tightly collimated jet, like water blasted through a. The math behind this idea is as elegant as it is radical. Plasma physicists argue that under the right conditions, a spinning torus of magnetized plasma can naturally pinch and twist magnetic field lines until they snap, releasing stored energy in a directed outburst. Sound familiar? It's almost identical to how white holes are theorized to behave, except here, the mechanism isn't warped spacetime, but raw electromagnetic fury. These plasma white holes wouldn't just mimic their general relativity counterparts. They'd outperform them, explaining not just jets, but also the bizarre energy signatures of quasars and active galactic nuclei without invoking unseen singularities. Critics are quick to point out the gaps. Plasma cosmology struggles to explain large-scale cosmic structures as precisely as the Standard Model, and dismissing black holes entirely requires ignoring decades of observational evidence, from gravitational wave detections to the eerie shadow of M87's supermassive black hole. But supporters counter that white holes in this framework aren't just placeholders, they're testable. If plasma vortices really power cosmic jets, their emissions should carry distinct electromagnetic fingerprints, like specific polarization patterns or energy distributions that differ from black hole-driven jets. Future telescopes tuned to these subtle signals might finally settle the debate. The real surprise: this hypothesis forces us to confront an uncomfortable truth. Our universe might be more flexible than we thought. Whether white holes are born from crumpled spacetime or spinning plasma, their theoretical existence challenges us to rethink not just how cosmic jets form, but what's possible at the extremes of physics. And that's a revolution worth watching, no matter which side of the fringe it comes from. The scale has long been our roadmap to understanding civilization's potential, from Type I, harnessing a planet's energy, to Type II, controlling a star's output. all the way to type III, commanding the power of an entire galaxy. But what if the ultimate energy source for these hyper-advanced societies isn't stars or dark matter, but something far more exotic? Hypothesis 18 dares to propose that white holes, those cosmic rebels defying gravity, could be the universe's ultimate power plants, fueling civilizations so advanced they'd make our wildest sci-fi look quaint. Picture a white hole not as a curiosity, but as a celestial battery, its endless eruptions offering energy outputs dwarfing even the quasars. Unlike black holes, which lock energy away, white holes are cosmic, blasting matter and radiation into space with unstoppable force. For a civilization mastering their physics, tapping that energy wouldn't just be an upgrade, it would be a paradigm shift. Imagine structures built around white holes like dams on a river, capturing their outbursts to power interstellar megaprojects. Swarms scaled to galactic proportions, quantum computers the size of star systems, or even engines capable of bending spacetime itself. The numbers are staggering. A single white hole's emission could outshine entire star clusters, offering energy budgets so vast they'd render traditional fuels obsolete. But here's the catch. Harnessing this power would require technology bordering on magic. White holes don't just emit energy, they do so violently, in unpredictable bursts that could vaporize anything within light years. A type III civilization might need to stabilize them first, perhaps using gravitational lenses or quantum fields to tame the eruptions, turning chaos into a steady current. Some models suggest that advanced beings could even manipulate spacetime to create artificial white holes, tiny, controlled versions acting as renewable energy cores. It's the ultimate flex of cosmic engineering, not just using what the universe provides, but bending its rules to forge new utilities. The implications ripple beyond energy. If white holes can be harnessed, they might also serve as cosmic beacons, their high-energy emissions detectable across the universe. SETI researchers have long scoured the skies for alien radio signals, but what if the real signatures of advanced life are white hole-driven energy grids, flashing like lighthouses in the void? Unexplained gamma-ray patterns or anomalous particle streams could be the smoking guns, evidence of civilizations operating on scales we're only beginning to fathom. Yet the skeptics raise valid concerns. White holes remain theoretical, and even if they exist, their volatility makes them seem more like cosmic bombs than batteries. But history shows us that impossibility is often just a matter of perspective. To a Bronze Age human, nuclear fission would have been unimaginable. To us, white hole engineering might feel equally out of reach. The difference is scale and time. A civilization millions of years older than ours might see these objects not as dangers, but as tools, as mundane as we find wind turbines or solar panels. Whether this hypothesis is visionary or fanciful, it forces us to confront a humbling truth. The universe's greatest resources might not be stars or planets, but the phenomena we've yet to understand. And if white holes really can power galaxies, they're not just cosmic oddities. They're the ultimate keys to a future we're only beginning to dream of. Entropy is the universe's strictest accountant, keeping track of every particle's messy descent into chaos, or so we thought. Hypothesis 19 throws a wrench into this cosmic ledger, suggesting white holes might be the ultimate rule breakers, defying the arrow of time itself. While the rest of the universe marches forward, surrendering to disorder, these enigmatic objects could be carving out pockets where time runs backward, spewing perfectly ordered matter like cosmic rewinding machines. Imagine a waterfall defying gravity, its droplets not falling but rising. White holes might be doing the thermodynamic equivalent, turning the universe's relentless slide into chaos on its head. At the heart of this idea is entropy's ironclad rule. Systems always move from order to disorder. A shattered glass doesn't reassemble itself. Smoke never flows back into a cigarette. But white holes don't play by those rules. Their explosive ejections, streams of matter arranged with eerie precision, could represent localized entropy decreases, like finding a frozen pond in the middle of a desert. To an outside observer, this would look like time reversing within the white hole's influence. Particles wouldn't just emerge, they'd seem to, reconstructing themselves into states of higher order as if the universe hit rewind. Its thermodynamics turned inside out, and the implications are staggering. Consider a thought experiment. A white hole erupts, spraying a perfectly aligned beam of hydrogen atoms into space. In our universe, those atoms should eventually disperse, mixing with interstellar gas in a slow dance toward chaos. But what if the white hole's outburst resets them to an earlier, more ordered state? It's as if you dropped a deck of cards and watched them not scatter, but neatly stack themselves midair. This isn't just defying entropy, it's mocking it, creating bubbles where cause and effect might temporarily flip. Physicists are torn between fascination and horror at this possibility. On one hand, it offers a loophole in the second law of thermodynamics, suggesting entropy isn't absolute, just overwhelmingly likely. On the other, it opens existential questions. If white holes can locally reverse time's arrow, does that mean the universe has built-in undo buttons? Could advanced civilizations harness these regions, creating enclaves where aging pauses or even reverses? The math doesn't rule it out, but the philosophical implications are dizzying. Critics argue that any entropy decrease in a white hole's outburst would be offset by a greater increase elsewhere, preserving the universe's overall slide toward disorder. Yet supporters counter that even temporary, localized reversals would rewrite our understanding of time's flow. Imagine a white hole's ejecta as a message in a bottle from the past, not just preserving information, but actively restoring it to a prior state. The effect might be fleeting, but its existence would prove that time's arrow isn't immutable, just statistically favored. The real test lies in observation. If white holes truly create pockets of backward entropy, their emissions should carry signatures of impossible order, particle streams with unnatural coherence, or energy distributions that defy thermodynamic predictions. Future telescopes tuned to quantum-level details might spot these anomalies, catching the universe in the act of breaking its own rules. Until then, the hypothesis stands as a thrilling provocation, proof that even time itself might be more flexible than we ever dreamed. And if that's true, the cosmos just got a lot stranger and a lot more interesting. What if the Big Bang wasn't the beginning, just a single note in an endless cosmic symphony? Hypothesis 20 takes us back before time itself, proposing that white holes might not just exist within our universe, they could be the very seeds that birthed it. Imagine a reality where universes bloom like flowers in an infinite garden, each one sprouting from the explosive eruption of a white hole in a parent cosmos. This isn't just a tweak to cosmology, it's a complete reimagining of existence, where our universe is just one link in an unbreakable chain stretching eternally backward and forward. The idea hinges on a radical rewrite of the Big Bang narrative. Instead of a singular, inexplicable explosion, our universe might have emerged from a white hole's violent outburst in another, older reality. Picture it like a cosmic matryoshka doll, each layer containing another, smaller world, with white holes acting as the birthing channels between them. In this cyclical model, black holes in the parent universe could collapse to critical density, then rebound as white holes, ejecting their contents not into empty space, but into a newborn spacetime continuum. The matter and energy we see around us, every star, every atom, might just be the recycled remnants of a universe that came before. This vision dovetails with cutting-edge theories in quantum gravity, where singularities aren't dead ends but turning points. Just as a compressed spring eventually snaps back, a collapsing black hole might reach a point where quantum effects overpower gravity, triggering a white hole explosion, and with it, the birth of a new cosmos. The math suggests something astonishing. The physics inside a rebounding singularity could naturally reset constants like the speed of light or the strength of gravity, explaining why our universe has the precise parameters needed for life. It's not fine-tuning, it's cosmic inheritance. The implications are staggering. If white holes spawn universes, they're not just objects, they're architects, shaping the fundamental rules of reality with each new cycle. Our universe's flat geometry, its uneven distribution of matter, even the mysterious dark energy accelerating its expansion. These might not be random features, but echoes of the white hole that birthed us. Some theorists go further, suggesting that subtle anomalies in the cosmic microwave background, the afterglow of the Big Bang, could carry fingerprints of this primordial white hole, like a birthmark stamped onto spacetime itself. Yet the challenges are just as profound. Without a way to observe beyond our universe's boundaries, how could we ever test this idea? Some clues might lie in the behavior of black holes, particularly those that seem to disappear without the expected Hawking radiation. Could these vanishing acts be black holes transitioning into white holes in another reality? Others propose that quantum entanglement, spooky action at a distance, might be a remnant of pre-Big Bang connections, threads of causality stretching back through the white hole's eruption. Whether this hypothesis is visionary or speculative, one thing's certain: it transforms white holes from cosmic curiosities into something far grander. They're not just rebels against gravity, they're the universe's way of reinventing itself over and over in an endless dance of creation. And that changes everything. The theory of general relativity has reigned supreme for over a century, the gold standard explaining everything from falling apples to colliding black holes. But what if gravity isn't quite what we think? Hypothesis 21 ventures into the controversial realm of modified gravity theories, where the rules bend and warp in ways never imagined, and where white holes might emerge not as cosmic anomalies but as inevitable predictions. In these alternative frameworks, from MOND to scalar tensor theories, white holes aren't just possible, they could be unavoidable, rewriting the cosmic rulebook in the process. Take MOND, modified Newtonian dynamics, a rebel theory that ditches dark matter entirely, proposing instead that gravity behaves differently at colossal scales. In this framework, the rotational speeds of galaxies don't require invisible matter to explain their motion. They're the result of gravity itself changing its tune in the cosmic deep. But here's the twist. If gravity's laws are fluid, the conditions for white holes could become far more permissive. Without the strict singularity constraints of general relativity, spacetime might fold and fracture in unexpected ways, creating natural escape hatches where matter bursts outward instead of collapsing inward. Picture a dam breaking not from pressure, but because the river itself decided to flow uphill. The implications are explosive. If white holes exist in MOND or similar theories, their discovery wouldn't just add a new object to the cosmic menagerie. It would obliterate the need for black hole singularities altogether. Suddenly, the universe's most terrifying objects might just be white holes in disguise, their event horizons illusions born from our incomplete understanding of gravity. It's a double revelation, proof that dark matter isn't the only way to explain galactic behavior, and that's gravity, while brilliant, might be just the first verse in a much longer song. But the real shockwave would ripple through the foundations of physics itself. For decades, general relativity has been the unchallenged language of spacetime. If white holes emerge naturally in modified gravity frameworks, they'd force us to confront an uncomfortable truth, that our cosmic equations are approximations, not absolutes. The very fabric of reality might operate by rules we've yet to fully grasp, with white holes as the stone translating between old and new paradigms. Imagine the irony. Objects once dismissed as mathematical oddities becoming the key to unlocking gravity's true nature. Critics, of course, remain skeptical. Modified gravity theories struggle to explain phenomena like the bullet cluster, where colliding galaxies seem to fling dark matter ahead of visible matter like cosmic confetti. Yet supporters counter that white holes in these frameworks could offer alternative explanations. Perhaps what we interpret as dark matter's gravitational grip is actually the subtle influence of white hole remnants, their repulsive gravity subtly nudging stars and gas in unexpected ways. The debate rages on, but one thing's certain. If a white hole is ever found where relativity says it shouldn't exist, the universe just got a lot more interesting, and our understanding of it a lot more humble. The hunt for answers is already. Astronomers scour galaxy rotation curves for deviations that might hint at modified gravity's fingerprints. Theorists run supercomputer simulations, testing whether white holes could form naturally in these alternative models. And lurking in the background is the tantalizing possibility that somewhere out there, a white hole is waiting to be discovered, not as a relic of sequations, but as a herald of the next great physics revolution. After all, science progresses not by clinging to old truths, but by daring to ask, what if we've been wrong all along? The black hole firewall paradox is one of the most unsettling puzzles in modern physics, a cosmic nightmare where the rules of quantum mechanics and general relativity clash head-on. According to this idea, the event horizon of a black hole isn't just a point of no return, it's a searing wall of energy, incinerating anything that crosses it. This fiery fate preserves quantum information but torches vision of smooth, uneventful spacetime. It's a paradox with no easy solution, unless white holes step in as the universe's ultimate peacekeepers, offering a way to reconcile these warring laws with their own paradoxical physics. Here, where the plot thickens. If a black hole's event horizon is a firewall, its white hole counterpart could act as an information repair shop, meticulously reconstructing scrambled quantum data before ejecting it back into the cosmos. Picture a cosmic assembly line where matter isn't just destroyed but refurbished, like a factory that melts down old cars and spits out pristine new ones, complete with every original bolt and scratch. In this scenario, white holes wouldn't just resolve the firewall paradox. They'd turn it into a feature, not a bug. The searing destruction at a black hole's edge would be balanced by the white hole's meticulous reconstruction on the other side, preserving the universe's quantum ledger without violating relativity's rules. The elegance of this idea lies in its symmetry. Black holes and white holes, long seen as opposites, might actually be partners in a grand cosmic conservation scheme. One shreds information into chaos, the other stitches it back together. The firewall, once a threat to physics' foundations, becomes a necessary step in the process, a crucible where information is purified rather than lost. It's as if the universe encoded it into its own laws, ensuring no data ever truly vanishes, just transforms. But how would this work in practice? Quantum mechanics demands that information be preserved, but general relativity insists that black holes erase it. White holes bridge the gap by acting as quantum error correctors. As matter falls into a black hole, its information gets scrambled like a shattered hard drive. But if that data is funneled through a white hole, perhaps via a wormhole or quantum entanglement, it could be reassembled in the eruption like a puzzle solving itself midair. The result: a universe that never forgets, where every particle's history is archived in the fabric of spacetime itself. Critics argue this is a band-aid on a deeper wound, that white holes merely shift the paradox rather than solve it. Yet supporters counter that the math holds up. In certain loop quantum gravity models, white holes naturally emerge as the other side of black hole evolution, their firewalls not destroying information but resetting it. The real test may come from gravitational wave astronomy. If detectors ever catch echoes in black hole merger signals, subtle ripples that shouldn't exist under classic relativity, it could hint at white holes lurking in the shadows, quietly tidying up the universe's loose ends. Whether this hypothesis is a temporary fix or a revelation, one thing's clear: white holes aren't just cosmic oddities. They're potential peacemakers in physics' longest war, proof that even the universe's most violent contradictions might have a resolution hiding in plain sight. And that changes everything. What if the universe isn't just a cold, mechanical machine, but a vast, thinking entity? Hypothesis 23 dives into the deepest waters of speculation, where physics meets philosophy in a radical proposition. White holes might not just shape spacetime, they could be the cosmic scaffolding of consciousness itself. At first glance, it sounds like science fiction, but the idea isn't entirely fringe. If consciousness arises from the fabric of reality, as some quantum mind theories suggest, then these gravitational rebels could be the universe's way of thinking out loud, emitting not just matter, but the raw potential for awareness. Picture consciousness not as a byproduct of brains, but as a fundamental feature of the cosmos, woven into spacetime like gravity or electromagnetism. In this view, the universe isn't just alive, it's awake, and white holes might be its neurons firing. Their explosive outbursts could be more than ejections of energy. They might be moments where the universe's underlying mind becomes tangible, translating quantum fluctuations into something resembling thought. It's a wild leap, but the math gets eerily suggestive. Quantum field theory allows for information to propagate in ways that resemble neural networks, and white holes, with their ability to rewrite spacetime's rules, could act as cosmic synapses, connecting distant regions of reality in a web of potential sentience. The implications are dizzying. If white holes play a role in consciousness, they might explain mysterious phenomena like intuition, or not as glitches in our brains, but as fleeting interactions with the universe's own processing. Near-death experiences, where people report transcendent visions, could be moments when the brain taps into the white hole's informational torrent, like a radio briefly tuning into a cosmic broadcast. Even creativity might get a rewrite. What we call inspiration could be the mind aligning with these spacetime thought emitters, drawing ideas from the universe's deeper layers. Critics, of course, dismiss this as metaphysical hand-waving. Consciousness is messy enough without dragging white holes into it, and there's zero empirical evidence linking the two. But supporters counter that the absence of evidence isn't evidence of absence, just a sign we're asking the wrong questions. If consciousness is truly fundamental, we might need new tools to detect it, instruments sensitive not just to particles and forces, but to the subtle patterns of information that could underlie awareness. Future experiments in quantum biology or neural physics might uncover hints of this connection, like anomalies in brain activity that correlate with distant cosmic events. The debate stretches beyond science into philosophy's oldest questions. What is reality? What is thought? If white holes are part of the answer, they're not just cosmic oddities, they're mirrors reflecting the universe's deepest mystery back at us. And that's a hypothesis worth exploring, no matter how far out it seems. After all, if the cosmos can birth black holes and warp time, why not consciousness too? The truth might be stranger than we've dared to imagine. For over a century, astronomers have painted black holes as the architects of galaxies, dark engines lurking at galactic cores, their gravity shaping star formation and cosmic evolution. But what if we've had it backward? Hypothesis 24 flips the script entirely, proposing that white holes, not black holes, might be the true hearts of galaxies, They're explosive energy birthing stars and sculpting cosmic structures on scales we've barely begun to comprehend. Imagine a galaxy not as a vortex spiraling toward darkness, but as a radiant bloom growing outward from a brilliant, energetic core, a cosmic lighthouse broadcasting the seeds of creation across the void. This radical idea starts with the puzzle of star formation. Traditional models struggle to explain how diffuse gas clouds collapse into stars fast enough to match what we observe. But if a white hole sat at a galaxy's center, its relentless outward energy could solve the mystery. Picture a shockwave rippling through interstellar gas, compressing it just enough to trigger stellar birth. Unlike black holes that devour matter, white holes would fertilize their surroundings, their high-energy jets acting like cosmic plows, churning gas into dense pockets ripe for star formation. The math is tantalizing. Simulations show that such outbursts could create the precise conditions needed for rapid star birth, matching the frenetic pace seen in young galaxies. The implications rewrite galactic history. If white holes anchor galaxies, their energy output might explain why some galaxies, like quasars, burn so fiercely in their youth before settling into quieter maturity. The white hole's initial eruptions would flood the galaxy with radiation and particles, igniting star factories and supercharging magnetic fields. As the white hole's energy wanes over eons, the galaxy would gradually transition to black hole dominance, like a brilliant torch passing its flame to a smoldering ember. This could solve another long-standing puzzle: why early galaxies seem to form stars far more efficiently than modern ones. The answer might lie in the white hole's fading glow, its golden age of creation giving way to a quieter, darker era. Observational clues are already hiding in plain sight. Some active galactic nuclei, the bright cores of distant galaxies, exhibit energy signatures that don't quite fit the black hole model. Unexplained particle jets or peculiar radiation patterns could be the fingerprints of white holes, their unique physics leaving traces in the light we detect. Even the Milky Way's core holds mysteries, strange gamma-ray bubbles and unexpected magnetic structures that defy simple explanations. Could these be relics of an ancient white hole, its energy now dimmed but its influence still etched into our galaxy's bones? Critics argue that white holes lack the gravitational punch to shape galaxies as profoundly as black holes. But supporters counter that gravity isn't the only force at play, energy matters just as much. A white hole's repulsive output could sculpt gas clouds and star clusters through radiation pressure and particle winds, achieving similar large-scale effects without relying solely on gravity's pull. It's a cosmic tango of push and pull, where creation and destruction dance in ways we're only beginning to map. The most mind-bending possibility: if white holes seed galaxies, our entire cosmic neighborhood, every star, every planet, even us, might owe its existence to one of these primordial eruptions. We could be living in the aftermath of a white hole's creative fury, its echoes still resonating in the spiral arms of our galaxy. That's not just a new model of galactic evolution, it's a new origin story for everything. And if future telescopes catch a young galaxy in the act of formation, its core ablaze with the unmistakable signature of a white hole's outburst, it wouldn't just change astronomy. It would redefine our place in the cosmos. What if the universe isn't just governed by physics, but by code? Simulation theory, the mind-bending idea that reality might be an advanced digital construct, has long flirted with the edges of science and philosophy. But here, where it gets wild. If we are living in a simulation, white holes could be the ultimate glitches in the system, cosmic rendering errors where the universe's underlying programming leaks through. Think of them not as natural phenomena, but as digital artifacts, like a video game struggling to load a texture or a corrupted file spitting out garbled data. In this framework, white holes aren't just defying gravity, they're exposing the seams of the simulation itself. Picture a universe running on incomprehensibly advanced hardware, where the laws of physics are just lines of code. Most of the time, the program runs smoothly. Stars burn, planets orbit, black holes swallow matter without a hitch. But every so often, the system hiccups. A black hole's calculations overload, or a quantum fluctuation slips through an unchecked variable. The result: a white hole, an unintended overflow, where the simulation's logic fails to fully delete matter, forcing it back into the game world in a burst of error messages made manifest. These wouldn't just be random glitches. They'd be the universe's version of a debug log, revealing the hidden syntax beneath reality. The implications are staggering. If white holes are rendering errors, their properties start to make eerie sense. Their sudden, unpredictable outbursts mirror the way software crashes, unexpected, violent, and impossible to replicate on demand. The fact that we've never observed one directly could mean they're patched quickly, like a cosmic programmer hot-fixing the code before players notice. Even their defiance of entropy fits. In a simulation, energy conservation might not be a physical law, just a guideline, one that breaks when the system's memory management falters. This idea dovetails with some of simulation theory's most provocative claims. Proponents argue that if the universe is programmed, we should occasionally find anomalies, places where the rules bend or break. White holes fit the bill perfectly. Their existence challenges fundamental physics, much like a bug challenges a game's engine. Some theorists even suggest that white holes, energy signatures, could carry hidden patterns, like error codes embedded in their radiation. If we ever decode those patterns, we might uncover the universe's source language, the ones and zeros underpinning everything. Of course, skeptics dismiss this as speculative fiction. Without direct evidence, equating white holes to software glitches is closer to philosophy than physics. But supporters counter that absence of proof isn't disproof, it's a challenge to look deeper. Future experiments could search for unnatural regularities in cosmic rays or gravitational waves, hints of algorithmic processes beneath the chaos. Even if the simulation hypothesis remains unproven, white holes force us to confront a humbling question. If the universe were programmed, how would we know? And what if the answers are already flashing in the void, waiting for us to debug the cosmos? Whether you buy the simulation angle or not, one thing's clear. White holes don't just challenge our understanding of physics. They challenge our understanding of reality, and that's a mystery worth chasing, no matter where it leads. The universe has a rhythm, a heartbeat of creation and destruction that's played out for billions of years. But what if that rhythm isn't just a cycle? What if it's a loop, an endless echo where every ending is just a new beginning in disguise? Hypothesis 26 takes this idea to its most breathtaking extreme, suggesting that white holes might not just be cosmic anomalies. They could be the universe's ultimate reset buttons, the architects of existence itself. Imagine a future so distant that all stars have burned out, all black holes have evaporated, and the cosmos is little more than a cold, empty sea of fading radiation. In that darkness, white holes could be the spark that reignites everything, recycling the ashes of the old universe into the fire of a new one. This isn't just poetic speculation, it's grounded in the eerie symmetries of physics. If black holes are the universe's trash compactors, crushing matter into oblivion, white holes would be their cosmic counterparts, it back into being. The math suggests something astonishing. When a black hole fully evaporates via Hawking radiation, its final moments could trigger a quantum rebound, a bounce so violent it flips the collapse inside out. Instead of vanishing into nothingness, the black hole's remnants might transform into a white hole, erupting with all the energy it once swallowed. Now scale that up. If every black hole in the universe eventually undergoes this transformation, their combined white hole outbursts could flood the void with enough energy and matter to trigger a new Big Bang, not from nothing, but from everything that came before. The implications rewrite the story of cosmic doom. Instead of a heat death where the universe fades into eternal stillness, we'd be looking at a rebirth death where collapse and renewal are two sides of the same coin. Picture it like a phoenix made of spacetime. The universe doesn't die, it combusts, leaving behind a seed that grows into a fresh cosmos. This idea, known as conformal cyclic cosmology, turns white holes into cosmic, bridging the gap between one universe and the next. Their eruptions wouldn't just be random events. They'd be the universe's way of hitting plus alt plus del on itself, starting the story over with a new set of physical constants, new laws, perhaps even new dimensions. But here's the most mind-bending part. If this hypothesis is true, our universe might not be the first. It could be one in an endless chain, each born from the white hole remnants of the last. The atoms in your body, the light from distant galaxies, all of it might be recycled stardust from a previous iteration of reality, transformed but never truly gone. Some theorists even speculate that subtle anomalies in the cosmic microwave background, the afterglow of our Big Bang, could carry imprints of that prior universe, like scars from a life before time. Of course, the skeptics have their doubts. The energy required to trigger a new Big Bang is unimaginable, and the mechanics of white hole rebirth remain speculative at best. Yet the elegance of the idea is undeniable. It solves one of cosmology's greatest puzzles, the fate of the universe, not with a whimper but with a bang. And if the universe really is cyclical, then white holes aren't just oddities. They're the hidden gears of eternity, turning the wheel of existence again and again. The ultimate question isn't how it all ends, it's how many times the story's already been told. From the ashes of dying black holes to the seeds of entirely new universes, white holes have taken us on a journey through the farthest reaches of scientific imagination. These 26 hypotheses aren't just wild guesses, they're the bleeding edge of physics, where the known laws of reality bend and twist into something unrecognizable. Whether they're real or not, one thing's undeniable. White holes force us to confront how little we truly understand about the cosmos. They're cosmic riddles wrapped in enigmas, each one daring us to rethink everything from the birth of time to the fate of existence itself. Think about what that means for a moment. Every white hole theory, whether it's a gateway to another dimension, a dark matter factory, or a glitch in the universe's code, isn't just a story. It's a challenge to gravity, to quantum mechanics, even to our most basic assumptions about cause and effect. These ideas don't just push boundaries, they obliterate them, revealing a cosmos far weirder, more dynamic, and more alive than we ever imagined. And that's the real magic here. White holes aren't just objects, they're invitations. Invitations to explore, to question, to wonder what else might be hiding in the shadows of our understanding. So where do we go from here? The hunt for answers is already. Telescopes scan the skies for unexplained bursts of energy that could be white holes calling cards. Supercomputers simulate their hypothetical physics, probing how they might reshape spacetime. Theorists wrestle with equations that could one day turn these speculations into solid predictions. And you, yes, you are part of this story too. Every time you gaze up at the night sky and wonder what's out there, you're joining a centuries-old quest to unravel the universe's deepest secrets. That's why we want to hear from you. Which of these white hole theories blew your mind the most? Are you team quantum time capsule or team multiverse portal? Maybe you've got a wild hypothesis of your own. Drop it in the comments. We're all craving fresh perspectives on these cosmic puzzles. And if you're hungry for more mind-bending space mysteries, hit that subscribe button. The universe isn't done surprising us yet, and neither are we. Until next time, keep your eyes on the cosmos. Who knows? The next great discovery might be hurtling toward us right now, spat out from a white hole we've yet to find. The adventure